Hi, this is Rebecca, and I'm going to be talking about momentum. So what I struggled with on the momentum test was impulses and force, change of direction, basically momentum after different rebounds, and overall in physics I seem to find the free response problems more challenging than multiple choice. So for this video I've chosen 3 different free response problems that I will be going over. First, and there's a problem like this problem similar to this on the test. A woman and her son are on a skating rink, and they start at rest, and then they push against each other for a period of time, 0.6 seconds, and then they separate. So part A says to calculate the speed of the son after the push. So we're given the tools to calculate the momentum of the mother, and we know the mass of the son. So we just say that the velocity, so we have to know that change in momentum is always conserved. So we can set the momentums equal to each other, and we say the velocity of the son equals the mass of the mother times the velocity of the mother over the mass of the son. We can plug in the numbers they gave us, and our answer should be the velocity of the sun is equal to 1.1 meters per second. Part B says calculate the magnitude of the average force exerted on the son by the mother during the push. So we know that the average force times time is equal to P, or change in P, and change in P is impulse. So we can solve this and try to change around, and we know that our average force is equal to change in momentum, which is mass times the change in velocity over time. And we can plug in the information they gave us in the problem, and we know that our force is equal to 64.17 newtons. So the important idea here is that force is related to our change in momentum, which is an impulse, and you also need time to calculate those. Now part C says how do the magnitude and direction of the average force exerted on the mother by the son during the push compare to those of the average force exerted on the son by the mother. Justify your answer. So mathematically we can look at this and say we know the time is the same because they both are pushing for 0.6 seconds, and also because of conservation of momentum, these two changes in momentums should be equivalent. Now, we also know from our forces unit that Newton's third law says for every action there is an equal and opposite reaction. So we know that the forces have to be equal, and they also have to be in opposite directions. Okay, we're going to move on to another free response problem, the 2002. And it says you have a 2 kilogram frictionless cart moving at a constant speed of 3 meters per second, and it collides with a second cart of unknown mass, which is initially at rest. And the force is shown as a function of time on the graph below. At t0 is when the initial contact begins, and after the collision, the second cart requires a speed of 1.6 meters per second to the right. Assume friction is negligible during the collision. So part A says calculate the magnitude and direction of velocity of the 2 kilogram cart after collision. So this originally tripped me up for a little bit, but I think I finally got it. So we have to originally say that our change in momentum is equal to the impulse, or the force times the change in time, because that's the graph they give us. And it's important to know that the area underneath a force time graph is the impulse. So to take the area of that, we can just do 1/2 base height. So 1/2, 1 second, 10 newtons. And we find that our change in momentum is 5 newton seconds. And we know our change in momentum is equal to our final momentum minus our initial momentum. So we can solve that and say that our final momentum is equal to our initial momentum plus our change in momentum. So we can plug in all the numbers they gave us for this. But what's important to note is I plugged in a negative 5 newton seconds here, because we know that the impulse will be negative on the first cart in the system. So we solve this and we get 0.5 meters per second to the right is what the velocity of this car after impact. So we'll keep moving this way, just at a much slower speed. So part B is asking us to calculate the mass of the second cart, which was unknown. So this is important because it's a conservation of momentum problem, and what we need to do is we set the initial momentum, which of both carts, equal to the final momentum. And since one of them was at rest, that goes to 0. So it's just 2 kilograms times 3 meters per second. And then the final is the mass of the second car times the final velocity, which we calculated down before, and then the mass and the final velocity of the unknown mass, which they gave us in the problem. So we plug in all of our numbers, and we find that mass is equal to 3.125 kilograms. Now we're going to move on to a 1992 free response problem. And it reads, a 30 kilogram child is moving at 4 meters per second, jumps onto a 50 kilogram sled that is initially at rest on a long frictionless horizontal sheet of ice. Determine the speed of the child's sled system after the child jumps onto the sled. So an important thing that kind of comes to mind when you're first reading this is elasticity. So you know that you have two objects that are separate and they come together into one object. And this is called a perfectly inelastic system. And that will be pretty important later in this problem. So to solve this, we're going to use conservation of momentum again. Initial momentum, change in initial momentum equal to change in final momentum. We plug in, we can separate that into the child, momentum of the child, momentum of the sled, which was at rest, and then final velocity. And it's important that we plug in both the masses here because it's a velocity, but since they became one object, you have to add the masses together. So we can get final velocity is equal to momentum of the child over the total mass. And if we still use variables, and then we plug in all of our numbers and get 1.5 meters per second for the final velocity of the sled and the child together. Part B says, determine the kinetic energy of the child's sled system after the child jumps onto the sled. So, since I said it was perfectly inelastic, that means kinetic energy is not conserved in the system. But for this problem, all we have to do is say K equals 1/2 mv squared. And since we're looking at the entire system, we want to add the masses together. Final velocity we solve for in part A. Plug in all of our numbers, and Ke equals 90 joules. Now, part C is saying determine the speed of the sled after the child jumps off it. So basically what happened up here was after a short time, the child jumps off the sled, so she's at rest with respect to the ice. So we have conservation momentum right here, but we're doing it kind of the opposite way this time. So the mass of the child and the sled together times their velocity, and then the child goes to rest. So the momentum of the child is 0 plus the momentum of the sled. So we solve for the velocity of the final velocity of the sled. So we have total momentum of both objects together divided by the mass of the sled. We plug in all of our numbers and we find that our final velocity of the sled is 2.4 meters per second. So part D is saying determine the kinetic energy of the child's sled system, which is at rest at ice. So we have to add the kinetic energy together. So we have the kinetic energy of the child, who's at rest, so 0, plus the kinetic energy of the sled, which we can calculate by 1/2 mv squared. Plug in all of our variables we solved for earlier, and we get kinetic energy is 144 joules. Well, that's weird because earlier we had found that the kinetic energy was 90. So the next one asks us to determine what happened to the energy. Where did the increase come from? And why was there a change in energy? So we know that we're allowed to have a change in kinetic energy because it was perfectly inelastic. But since the child came to rest, a negative force had to be applied for the child to deaccelerate and come to rest. So according to Newton's third law again, for this negative force, there must be an equal and opposite positive force. So the positive force will accelerate the sled and create more kinetic energy. So that's where our increase of kinetic energy came from. So this has been my momentum video. I hope it helped.